join in. Let me first start the live streaming. Okay. Namaste, good evening and good morning to our colleagues and participants from US. Welcome to the IPA APS webinar towards gender equity, new directions and steps, second part today. I am Vandana Nanal, General Secretary of Indian Physics Association, IPA, and Professor at TIFR. Today we have two lectures by eminent women scientists. Some of you may know them. This is Professor Shobana Narasimhan and Dr. Eva Silverstein. But others who don't know will hear about their fantastic work and also a bit about their journey. I'm sure these talks will be inspirational and motivating to the young researchers, particularly the women in the audience. Without further delay, let me now invite Professor Tanushree Sahadas Gupta to introduce today's first speaker. Professor Tanushree specializes in theoretical condensed matter physics. She is Vice President of Indian Physics Association and also recently taken charge as a director of SN Bose National Center for Basic Science Research. She has many laurels, so let me just briefly mention a couple of them. She's a fellow of all Indian Science Academies. She's fellow of the World Academy of Sciences and also the APS fellow. So over to you, Tanushree, to introduce today's speaker.
Thank you so much, Vandana. I guess it is always...
We can't, can you get a little louder? Yeah.
Yeah, I'll try to make it louder. Is it okay now?
Yeah.
So thank you, Vandana. It's always a pleasure if you get the opportunity of introducing your good friend. So I'm very happy to introduce Shavana. Shavana is a professor of theoretical sciences at Jawaharlal Nehru Center for Advanced Scientific Research in Bangalore. She was formerly the chair of the Theoretical Sciences Unit there and also Dean of Academic Affairs. She obtained her PhD degree in theoretical physics from Harvard University and her master's from Indian Institute of Technology in Bombay. She did her postdoctoral research at Brookhaven National Laboratory and the Fritz Haber Institute in Berlin. She has been very active in the cause of the women. She has been on several national and international committees to promote women in science, including the Working Group on Women in Physics of IPA and the Standing Committee on Women in Science of the Government of India. And she regularly conducts career development workshops for women in physics at the Abdus Salam International Center for Theoretical Sciences, ICTP, in Trieste, Italy. Her field of research is in scientific interest is in the area of computational nanoscience, on which today's talk will be based on. And she uses basically the first principles calculation to design novel nanomaterials. And her work has been recognized in terms of several awards and fellowships. I'll just mention only a few. She is the elected fellow of the Indian Academy of Sciences, Indian National Academy of Sciences. She is the international honorary member of the American Academy of Arts and Science, and she received the Marsic lectureship of the American Physical Society, and she also got the Institute Silver Medal for her master's work from the Indian Institute of Technology, Bombay. So with that few words, let me welcome Shavana to deliver her talk.
Thank you, Tanushree, for that very kind introduction. I'm getting some weird echo. Is it okay for everybody else? It's okay?
Sorry, I also got small echo. Let me just figure out. Yeah.
Yeah, I think it's okay now, though.
Yeah.
I'm very happy to be giving this lecture. I thank the organizers for inviting me to give this. Before I start, let me just explain my image on my cover slide. This is some work we did. I'm just trying to get the pointer. Showing copper nanoparticles on an alumina substrate. They are used as catalysts. And so the green atoms are copper and the purple atoms are oxygen. And so these copper nanoparticles get oxidized. Sometimes for some reactions, when you use them as catalysts, you want them oxidized. Sometimes you don't want them oxidized. And what we calculated was the temperature at which the particle transitions from being oxidized to being not oxidized. And we found that this temperature is very dependent on the precise number of atoms, the cap copper atoms in the nanoparticle. So this is related to this one atom at a time that's there in my title. I'll talk more about these kinds of ideas, but let me very quickly go through my academic trajectory. Tanushree already mentioned it. I grew up in what was then called Bombay, is now called Mumbai. Then I went to Harvard in the USA for my PhD, did one postdoc at Brookhaven National Lab, then a second postdoc in Berlin at the Fritz Haber Institute. And then I returned to the Jawaharlal Nehru Center in Bangalore in India. And that's where I still am. Just a little bit more about that trajectory, what it was like being a woman during that trajectory and how that shaped my ideas about women in science. I went to an all-girls Catholic convent school in Bombay. That over there is me. And I never felt in that school that there was anything that I could not do because of being a woman. We were trained to think that we were capable of doing anything we wanted. And therefore, it came as rather a rude shock when I went to what was called junior college, which is equivalent to the 11th and 12th grade, to St. Xavier's College in Bombay, where because of the combination of subjects I chose, I was in a class of 75 students, of whom only 4 of us were women. And because I did rather well academically, in fact, topped the class, I was essentially ostracized by the male students. And this was my first experience with what I call the loneliness of the female scientist. It was better in my bachelor's, but for my master's, I went to IIT Bombay. This is a picture of some of us female students there. That one over there is me. This is Sarita, who is now a professor at the University of Illinois at Urbana-Champaign. She was also elected along with me to the American Academy of Arts and Sciences last year. But this was a campus with only 5% women students, and it was quite a miserable experience in terms of gender equity and gender relations, etc. So this shaped my sort of feminist ideas even more. I then went to Harvard as a PhD student in 1985. How was it? We were a class of 30, of whom only 2 were women. The next year, it was again a class of 30, of whom 3 were women. So really appalling gender ratios. This is me at Harvard with 2 of the women from the year below, Elizabeth Simmons and Catherine Benson. We formed rather close bonds, and we decided to found a group called Women in Mathematical and Physical Sciences. It had the unfortunate acronym of WIMPs. At that time, we thought it was a funny joke. Now I'm not so sure it's that funny. and I continue to work with Elizabeth Simmons even today on programs to promote women in physics. When I was a postdoc, I got upset about certain things and turned that anger into a sort of constructive channel. Together with another woman postdoc at Brookhaven, Maya Paczewski, we made the suggestion to APS to start Griffith, which was an electronic bulletin board for women in physics that ran for some years. This was just around the time the World Wide Web was starting, so there was no real, there were no websites as such, there were no blogs, but through email, you could keep in touch. Women around the world could share their experiences of being a woman in physics. I'm now a professor at JNC in Bangalore. This is our beautiful campus. This is a picture of my group that was taken last year. Are things better now? In some ways, of course, they're better, but this is a picture taken at a conference I attended in Shanghai 11 years ago. And you can see that the gender ratios are still pretty appalling in our field. You have to really hunt to find any women in this photograph. I am hidden over here. That's me, one of the women. And there's one other woman, I think, over here. So it's not an unusual experience at all for me to be the only woman at a conference, the only woman speaker, the only woman attendee. Some of my frustration and anger with this situation, I have turned into what Tanushree mentioned, which is since 2013 at the International Center for Theoretical Physics in Trieste. I have been organizing together with Elizabeth Simmons, who was my friend and contemporary at Harvard, who I showed you her picture. We've been organizing these career development workshops for women in physics from around the world. We focus mostly on women from developing countries. So far, hundreds of women from, I think, over 80 countries have attended these workshops. So that's about women in physics. For the rest of the time now, I'm going to talk about physics, about my science. So what we do in my group is we aim to design new nanomaterials in silico, that is on the computer, using first principles techniques, that is density functional theory, and a process of rational design. I realize that this is a rather general audience and various parts of this sentence may not make much sense to everyone. And I am going to, over the next 10 minutes or so, just explain this sentence, what the different terms in it mean and why they are important. So first, what about materials and materials design? Why am I a material girl? Why do I design nanomaterials? So materials are so important that we use them to define human history and progress. So we, if we look at the great prehistoric ages, there's the Stone Age, the Copper Age, the Bronze Age, and the Iron Age, because those were the materials that humans learned to use in that time, and that was an important marker of progress. What is particularly interesting about these ages is the Bronze Age, and in a couple of slides, I will explain to you why I find that age the most fascinating. How many materials exist in nature? This is the periodic table, of course. And there are about 98 naturally occurring elements and about 4,000 naturally occurring minerals. But we can make new materials. So with these Lego blocks, this is a periodic table, and the elements of the periodic table the atoms of the periodic table are the building blocks with which we can design new materials. We can make new materials that do not exist in nature, that are not found occurring naturally. So how many of these have we already made? How many have people succeeded in making? Those already made already fill several volumes. These are the books called the Landolf-Bernstein series. Before the internet existed, if I wanted to look up an alloy or something, I had to go to a library and look it up, look up that particular alloy phase in these volumes, which fill several library shelves. How many can we make in principle? So it's been estimated that if you look at the possible crystal structures one could have and only stoichiometric compositions, then if you have 4 elements, it's been estimated that you can make about 3 times 10 raised to 11 such compounds. And if you have 5 constituent elements, then you can make 10 raised to 13 such compounds. So this is obviously an extremely huge phase space. And if we want to search it, it's going to be quite a Herculean task. How do we look here for something that has desired properties, something that's the best material for a given application? It seems absolutely impossible. So let me return to the Bronze Age. I told you I'm fascinated by bronze. The reason the Bronze Age is different from a material science perspective, as opposed to, say, the Iron Age or the Stone Age or the Copper Age, is that bronze does not occur naturally. It is made, it's a man-made material. It's an alloy of copper and tin, and it's harder than copper alone, and it does not rust, unlike iron. So there were Bronze Age weapons, for example, and can someone tell me that they can still hear me? Because I got a message that my internet connection is unstable.
No, you're fine. You're okay.
Okay.
Clear.
And
Yeah.
this is a famous statuette called the Dancing Girl of Mohenjo-daro, which is made of bronze. But how did they know? How did they decide? How did they discover that if you mix copper and tin, you would get this fantastic material called bronze? So if you look at history, I mean, we don't really know how they first made bronze, but all the materials that we have used so far through human history have been either accidental discoveries or they have been found by trial and error. So these are just 2 funny cartoons about not materials discovery, but the discovery of the wheel, saying that it might have been discovered by accident or by a process of trial and error. So how does this process of trial and error work? There's a famous example for the Haber process, which synthesizes ammonia from nitrogen and hydrogen. It's been suggested that it's the most important scientific discovery of the 20th century. And iron is used as the catalyst for this process. So how did they know to use iron? They tested in the lab about 2,500 materials, and they decided that iron was the best. Actually, they found osmium was the best, but there wasn't enough world supply of osmium. And so iron was a compromise between being a very good catalyst and being widely available and not too expensive. But what do we want to do now instead? We want to replace this trial and error or brute force method by what we call rational materials design. And this rational materials design requires a to and fro between theory and experiment. So I do computations. I'm a computational scientist. So why do we do computations? Computations today are generally much cheaper than doing experiments. One can work from home. I say that partly as a joke, but believe me, during the last 1.5 years, I have really grown to appreciate the advantage of being able to work from home. They're often much quicker than doing an experiment. They can lead to greater understanding. One can easily simulate conditions that can be very difficult to achieve in a lab. For example, very high pressures or very high temperatures or very high magnetic fields. One can switch off effects in a calculation, like you can switch off relativity, you can switch off magnetism, which you can't really do in a lab. I will show you an example of this later. And you can make predictions for experimentalists to verify. So how do we do this rational materials design in practice? We take a material A, a material B, a material C, and then we do computations on these materials. We analyze the results. These pictures are all from PhD comics, which I'm sure many of you are fans of. If you haven't seen them, I certainly strongly recommend this comics series. Then after the analysis, we obtain insight into the design principles and use that insight, leverage that insight to design a new material with desired properties. So how do we do these computations? We use density functional theory. So I'm going to tell you a little bit now about density functional theory. So the basic problem we want to solve is the quantum many-body problem. So you have a many-body system which consists of some number of nuclei and some number of electrons. And these interact via the Coulomb interaction. And examples of such systems are atoms, molecules, or condensed matter systems. And we know how to write down the equation for such a system. It's the Mealy electron Schrödinger equation, or if you're doing it relativistically, it would be the Dirac equation. But this is an equation we can write down, and we know that the solution should be properly antisymmetrized to satisfy the Pauli exclusion principle. Though we can write down this equation, it's extremely difficult to solve. So let's look at this equation a little more. If you have a material with n nuclei and small n electrons, the Hamiltonian consists of the kinetic energy of the nuclei, the kinetic energy of the electrons, a potential energy of interaction between the nuclei and electrons, and between the electrons and electrons. Usually we make the Born-Oppenheimer approximation so that you can separate out the electronic Hamiltonian. So the electronic Hamiltonian has the kinetic energy of the electrons, the potential energy of interaction between the nuclei and the electrons, and the potential energy of interaction between the electrons and electrons. And it is this term, this electron-electron interaction, which makes this a very hard problem to solve because it's a many-body term. And density functional theory is a way of including these troublesome electron-electron interactions. So what do you do in density functional theory? You use an approach called the Cohen-Sham equations. And what you do here is, I have an analogy now. It's a somewhat silly analogy. I'm not entirely sure whether it's politically correct, so we can discuss the political correctness of this after my talk, perhaps. So assume you have a system of people of two genders. So the blue men might be the nuclei, the red women might be the electrons. And they have complicated interactions between them. And the problem you're trying to solve is to arrange them so that you achieve globally optimal happiness. This is obviously a very hard problem to solve. And in density functional theory, or DFT as it's usually called, you replace it by this problem where you have the men, but you just have one woman and you have to put her where she's happiest. And this is obviously a much easier problem to solve. But you have to pay a price. There's a new interaction that's introduced, which I have graphically symbolized by putting face masks on the men. I will talk about that in a moment. So the person who developed this whole framework is Walter Cohen, shown here as a young boy, and when he received the Nobel Prize in 1998. He has a very inspiring personal story because he grew up in Austria. He was sent out on one of the kinder transport trains when I think he was 14 because he was Jewish to escape the Nazis. He went to England, but then when the war broke out, he was imprisoned, interred as an enemy alien, and then sent to a prison camp in Canada, which is where he became interested in mathematics and physics. So DFT is now so popular that if you look at the 10 most cited papers in the PhysRev journals, they are all related to one aspect or another of density functional theory. I mean, these papers have just tens of thousands of citations. The two papers by Walter Cohen are here. The reason they're not right at top of the list is that they're such famous papers that people usually don't even bother to cite them. So I told you that there is one price one has to pay, which is that you have to introduce a new interaction, which is what we call the exchange correlation interaction, which I represented by a face mask. Now, we know that there is a perfect form of this face mask so that the solution to the one body problem is exactly the same as the solution to the many body problem. We know this perfect form exists, but we do not know what it is. So this is an problem that remains to be solved. We have very good approximations, but we don't know the exact form yet. So if you were to design this perfect face mask, if you were to find it, then I'm pretty sure you would get a Nobel Prize. So what do we do in DFT? These are also called first principles calculations because the only input is atomic numbers and atomic masses. And then you crank through the whole machinery of DFT, and then you get your output. So what we usually do is we input a structure and a composition, do DFT computations. Depending on the system, these computations may be fast or slow. And the output is mostly very accurate results for total energy and properties of system. What kind of output do we get? We get the total energy, which is a very useful quantity. You can use it to calculate geometric structure. You get the charge density, which is also very useful. I put smiley faces for these two because these two are guaranteed to be exactly correct, assuming you have the exact exchange correlation functional. You also get electronic eigenvalues. This is also called the band structure. And why I put a slightly puzzled face here is because these are not guaranteed to be exactly correct, but in practice, they work extremely well, and so we use them all the time. And DFT codes can run even on a cell phone. This is a picture already several years ago, as you can see by the rather clunky cell phone that it's running on, but this is one of the famous DFT codes called Quantum Espresso running on a friend's cell phone. So now I want to tell you a little bit about why we do nanomaterials. So the advantages of going nano are obviously that you can have miniaturization. You also need less amounts of possibly costly materials. But more interestingly to the scientist is that you can get enhanced properties. like you can get a higher magnetic moment. Nanoparticles tend to be more reactive. Now, in my title, I had said one atom at a time. So when you're really at the ultra small nano limit, so you just have a few atoms in your particle, you can change the properties drastically by just adding or removing one atom. So this is the reactivity of gold nanoparticles. This is already surprising because macroscopically, gold is not reactive. It's only in the nano domain that it's reactive. So if you have 8 atoms, it's pretty reactive. It's a good catalyst. You have 7 atoms, it's a terribly poor catalyst. And if you have 9, again, the reactivity drops. So every atom counts. And this is a material called phosphorine, which is one of the new popular layered materials. It's formed of layers of phosphorus atoms. And depending on the number of layers you have, the band gap of the material changes a lot. So you see, if you have just one layer, so that's phosphorine, then this is 2 layers of phosphorine, 3 layers of phosphorine, 4 layers, 5 layers, the band gap changes hugely. So now I'm going to, in the remaining time, I'm going to tell you briefly about 5 examples from my work on designing novel nanomaterials. So showing again the sentence I showed earlier, that we aim to design new nanomaterials in silico, that is on the computer, using first principle techniques, density functional theory, and a process of rational design. Hopefully now this sentence makes some sense to you. So I will give 5 examples from our work over the past decade. I'll show you how we make a new material, tune charge, tune morphology, tune reactivity, tune diffusion and stability, and tune rotation. So the first example is, can we make a new material? So I told you that we can make alloys that don't exist in nature, but some alloys you can't make in 3 dimensions. For example, if you have iron and gold, they're immiscible. You cannot make a 3-dimensional alloy out of iron and gold. But we predicted that iron and gold will form a stable surface alloy. It's just a 2-dimensional alloy if you deposit a single atomic layer of iron and gold on a ruthenium substrate. Okay. And then this is my student Madhura who did those calculations. This is a scanning tunneling microscope image. The experiment was done by our collaborators in the group of Sylvie Rousset in Paris. So each of these black dots is an iron atom. It is surrounded by 6 bright dots, each of which is a gold atom. So we've succeeded in making an iron gold alloy in 2 dimensions. This is our theoretically simulated STM image of how this system would look. And we also understood why this system forms. It is stabilized by magnetism. So we could turn off the magnetism, turn it on in our calculation. If we turn it off, the system doesn't want to form. If we turn it on, it wants to form. Because when you make this system, each of these iron atoms, which is surrounded by 6 gold atoms, acquires a very high magnetic moment, and that lowers the energy of the system, which is why it forms. So that was the first example. The second example is whether we can control the charge state of a material. Okay, so this is cobalt phthalocyanine. It's a molecule. It has a cobalt atom in the center, surrounded by various other atoms, and we deposit it on graphene. Okay, graphene is a monolayer of carbon atoms, a single monolayer of graphite. Now, normally, this cobalt atom has an oxidation state of 0, but if you dope the graphene, that is, you replace one of the carbon atoms with not 1 nitrogen atom, but 2 nitrogen atoms, okay? And then put the cobalt phthalocyanine on this. Our experimental collaborators again, this is Jérôme Lagout's group in Paris. Their STS, scanning tunneling spectroscopy, suggested that the oxidation state changes to -1. The cobalt now has a charge of -1. And these were our calculations. So these pictures show charge being transferred from the substrate to the cobalt phthalocyanine. This is now a side view of the system. This is when there's only one nitrogen atom. This is when there are two nitrogen atoms. So again, every atom counts. And this blue blobs here show charge that has been lost from the substrate, and these red blobs here show charge that is gained by the molecule. So you see that significantly more charge is gained, electrons are gained when you have two nitrogen atoms in the substrate. So we can, and why do you want to do this? It's again believed that if you do this, it will be a better catalyst. So that's why you want to do this. So the next question is, can we change the shape of a material? Okay, so larger gold nanoparticles have three-dimensional shapes. They sort of clump up. And this is true both in the gas phase and when they're deposited on oxide substrates. But there's reason to believe that they will be better catalysts if they can instead be made to take flat pancake-like shapes. So let's look at this cluster, which has this nanoparticle, which is made up of 20 gold atoms. So if you have this three-dimensional shape, it is low in energy, both in the gas phase and on oxide substrates. But this planar shape is what we want. So can we somehow tilt the energy balance? Can we make this one lower in energy than this? So these are other people who have worked on this similar system and had various suggestions. So our suggestion, this is my student, Nisha Mammon, who worked on this problem, was that if you dope this system again, that is, you take some of the divalent magnesium atoms, which are colored gray in this picture, and replace them by trivalent aluminum atoms, which are colored purple here, then we thought that you would get a shape transition. It would go from this three-dimensional shape to this two-dimensional shape. Incidentally, if you look at Nisha's earrings in this picture, one of them is the three-dimensional shape of this nanoparticle, and the other is the two-dimensional shape of this particle. So we did the DFT calculation. We saw that if the doping concentration, the concentration of aluminum atoms, is less than 0.5%, then the three-dimensional shape is favored. So what is on this axis is the difference in energy between the planar shape and the tetrahedral shape, between the two-dimensional shape and three-dimensional shape. And this is the doping concentration, the concentration of aluminum atoms. So up to 0.5%, it is this three-dimensional shape which is favored. But if you dope at a percentage higher than that, then yes, we've succeeded in getting this one favored. And experiments were done on this system by the group of Freund in Berlin. So this is again an STM image where they showed that if you have an undoped oxide, in their case, this was calcium oxide, then the gold nanoparticles have these clumpy three-dimensional shapes. But if you dope the oxide, in their case, they use molybdenum as the dopant, then you get these flat nanoparticles. This is a zoomed in version, and these are only one atomic layer thin. So you again see that you get, we made a prediction yet again, and it was confirmed by experiments. So DFT is a very powerful technique. You can predict things, and then experimentalists can carry out experiments according to the predictions, following the predictions, and they often turn out to be right. I'll skip this slide, and I will just tell you here that I said that the reason we do this is that we believe they can be better catalysts. So we can actually compute barriers for reactions to take place. So this is the barrier. These two blue atoms are oxygen, and we calculate the barrier to dissociate the oxygen, to break the oxygen-oxygen bond. So on the undoped support, where you have the three-dimensional shape, this barrier is 0.68 electron volts, whereas on the doped support, where you have the flat shape, the barrier is significantly reduced to 0.29 electron volts. This means that this is a better catalyst than this, okay? So the next example I want to show you is whether we can understand the diffusion and stability of a material. So this is an electron micrograph of gold nanoparticles seen from above on an oxide support. And you see that they're moving, and they're moving together, and they're coalescing. So these two particles just fused together and formed a larger nanoparticle. And then these two will move together, and they will again fuse to form larger nanoparticles. So this process is called sintering. It's always energetically favorable for these nanoparticles to diffuse and then fuse together to form larger nanoparticles. But we don't want that. We want the advantage of them being smaller nanoparticles. So we need to understand this process. Are all metals equally likely to diffuse and sinter? Are all sizes equally likely to do so? We need to study this process. So we have studied this, for example, for platinum. So this is a single platinum atom moving on a magnesium oxide surface. This is an actual simulation. It's not just a cartoon animation. It moves by a process called hopping. We can calculate the energy as it moves along the surface, and the barrier that it has to surmount to diffuse along the surface, we find it as 0.88 electron volts. Now let's add another atom. So make it a dimer. So that is a particle with two atoms in it. Now you see it moves by quite a different process. It doesn't just hop along. It forms a it follows a cartwheeling motion. It's vertical, then it lies down, and then it stands up again. And this process has quite a different energy landscape, and the barrier is much lower. It's 0.42 electron volts. Let's add another atom. So it's a third atom, okay? And so now it's sort of walking along the surface, like, I don't know, those of you who are fans of the Star Wars movies, to me, this looked like what are called AT-AT walkers in the Star Wars movies. So it's sort of walking along the surface slowly and ponderously. And the barrier for this, again, we can calculate, and it's 0.6 electron volts. And now let's add a fourth atom. And so now you have what's called a tetramer, and you have yet a fourth way of moving along the surface. It rolls along the surface. And the barrier for this is 0.8 electron volts. So one can do this. We also considered some of the results in the literature, etc. And we found a initially very surprising result, which is if you take this diffusion barrier and we plot it against the melting temperature of the bulk metal, then we seem to get a strong correlation. But this scaling relation does not hold for the dimers. Now, because of lack of time, I can't explain to you why this holds. We understand why you get such a scaling relation. We also understand why it does not hold for the dimers. So this is a very useful thing. It tells you that if you want to prevent sintering, you need to take a material which has a high bulk melting point. We can also study the processes by which sintering happens. So for example, for platinum, we see that the sintering happens by one atom at a time being added, but in a weird way. It's not the single atom that moves and attaches itself to the larger particle. Instead, it's the larger particle which moves and attaches itself to the single atom. Whereas for gold, it's another kind of process, which is called particle migration and coalescence. I come to my last example now. So can we understand the movement of what are called molecular machines? So molecular motors are natural or artificial molecular machines that are, you find them in living organisms, and you can also make artificial molecular rotors. So these have continuous rotation under an energy input. So you have, this is an example, again, an STM picture of a molecular rotor where you have some sort of guest network, and inside this you have a rotor. So we looked at this particular system. It's an organic molecule with a long name, which I won't go into, but both the host and the guest molecules are the same species. The host molecules have been colored yellow just artificially in this picture, and the silver molecules are the guest molecules. And I have to, okay, so let me play the video. Oops, it doesn't work if I have the, okay, so here. Now this is an STM video, and you see that the rotors, these silver molecules, are rotating, but it's not a continuous rotation like the previous video. It's a kind of switching motion. Let me just show it to you again. You see that they're rotating, and we wanted to study this using density functional theory. So we could, the top picture shows you the rotation, and the bottom shows how the energy of the system changes as the rotation happens. So what you see is that you see that when these yellow and green lobes that you see sometimes are hydrogen bonds being formed between the guest and the host. And when these hydrogen bonds are formed, this energy of the system is quite low. And when these hydrogen bonds do not exist, the energy of the system is high. Okay, so we understand the energetics of this system, and we can also compute, obviously, the barrier for this rotation to happen. So from density functional theory, we get a barrier of 0.944 electron volts. And in the experiments, by seeing how often this rotation happens as a function of temperature, they can estimate an experimental energy barrier, and they get 0.95 plus or minus 0.07 electron volts. So this is an excellent agreement, much better than we expected to have, really. So I'm done. So the take-home message I want to leave you with is that density functional theory, when used in tandem with experiments, can be used very successfully to understand why materials possess the properties they do. It can be used to design novel nanomaterials with desired properties. And at the nanoscale, properties depend both on the material and on the exact number of atoms that you have in your system. These are my acknowledgements. These are my students who worked on these projects. This is Stefano De Gironcoli, with whom we worked on the gold nanoparticle work. These are the next group is the experimental collaborators in Paris. then the experimental collaborators in Munich, and then our funding agencies. I'm grateful to all these people and agencies. And thank you very much. I am done.
Thank you, Shobana, for a wonderful talk. It was really like the Lego game where you put together the various parts and build it, in such a complicated theoretical subject, making it so nicely and explaining it. Also, for keeping to the time, leaving us ample time for discussion. There is a couple of questions in chat box. I'll start with that, but I request all the audience members either to type a question or they can even raise hand, and we can, since we have time, we can let them ask the question themselves. So let me first start with a comment from YouTube. Manu Negi says that's extremely informative talk. And I then come to a question from Suchetna Chatterjee. How are the initial conditions taken care of? For example, how do we decide that if we want to make an alloy of gold and iron?
Okay, so in this case, we decided that we wanted to make something that was magnetic, because we were interested in applications for, say, magnetic recording devices or something like that. So we decided that we would take the ferromagnetic materials. So one constituent we thought of as iron or cobalt or nickel. And then we thought of different other metals that they could be alloyed with. And we actually did a search of various other metals based on various criteria like size, etc. But we were looking for things that don't make alloys in the bulk, but because we also had this other goal that we wanted to make a surface alloy of something that wouldn't make a bulk alloy, but would make a surface alloy. And we did some, it was rather rapid to do the screening in DFT. And then we, based on, say, 15 systems, we got some rules, we got some guidelines for what might be the systems that are likely to make alloys. And then we narrowed down on this system as the most promising system. And then we told the experimentalists, this is the system which we think you should focus on. And they did it and it worked. I should also mention that the reason this approach was taken was initially they had tried other systems just sort of randomly or whatever, and they hadn't worked. They hadn't succeeded in making an alloy. And that's why they decided to turn to DFT theorists and ask them to identify, ask them as in ask us to identify a promising system.
Thank
Chitra,
you.
You're muted. Yeah.
So just quickly, can I add one thing to it, Vandana?
Sure.
I have other questions. Thank you very much, Shobana. It's a wonderful talk. So would you, I heard something similar from Tanushri like a couple of years back on DFT modeling. So do you think the field is mostly driven by so it's an experiment that drives the what kind of materials you want to generate, or it's that you sort of design materials for certain kinds of purposes, and then you ask experimenters, or is it both way? I think maybe
it can be both ways. I mean, sometimes it's the theoretical prediction that comes first. Sometimes it's the experiment that comes first, or sometimes you work in parallel. Like I would say in my iron gold alloy work, we sort of worked in parallel, I would say. In our gold nanoparticle work, we made the prediction, published it, and then the experiment was done. In the case of the cobalt phthalocyanine, they did the experiment first and then asked us if we could support their findings and help explain them. So it really can be in many different ways.
Thank you. Very exceptional talk. Very nice talk. Thank
you.
We have a question from Tridip. Tridip, you want to ask the question? Yeah. Sorry, Trideep,
Yeah,
I think
I can read that. I can read it in the chat box. It says,
sure.
in DFT, I didn't understand how putting a single electron at a time helps reduce the complexity of the problem. Wouldn't the electrons, when put again together, interact with each other and make the problem complex again? No, that is exactly the point. It's not that you add one electron at a time. You just have one electron. You have a non-interacting electron problem instead of you replace the interacting electron problem by a non-interacting electron problem. And because they're non-interacting, you have to solve for just one electron. Okay. And the complexity you have is that you have this extra term, the exchange correlation term, which contains all the many body effects. But it's not that I solve for one electron and then I add the second electron and then I add the third electron or whatever. I just solve for one electron and that's it.
Thank you, Shobana. Shubhavati?
It says...
we'll get Shubhavati's first and then Madhurima's.
No, it was really a fantastic talk, Shobna. I really enjoyed it. Just, it was a curiosity, like with all this artificial intelligence and machine learning. So in this context, do you think that, that's going to greatly help in these active efforts or?
Oh, absolutely. So I didn't mention it at all because we haven't done it really except in one very small way. But that's the hottest trend, I would say, in DFT right now is combining DFT from machine learning. So I said, I had shown that we do this analysis and and gain insight. So far we had been doing that by ourselves by thinking, but now that step is being done through machine learning. You may not always gain physical insight by doing it, but that prediction of what you should then get, which will be your best material or whatever, is done through machine learning. And certainly very interesting predictions are coming out. It's sometimes I find a little intellectually dissatisfying because you don't gain that physical insight, which at least people of my generation like to get, but it's certainly working very well.
Thank you.
Yeah, there's one question from Madhurima. Madhurima, you want to ask or we should just read?
No, either way is fine. Hi, Shobna, that was a lovely talk. As a person who does some simulations and the experiments, one of the bigger problems I've had is while we could do the simulations, the experimental validation was always a problem, going back to the lab. Since you started off mentioning that this is like work from home friendly, how effective are these calculations in the absence of an experimental validation / for people from smaller places where we may or may not have extensive collaborations and who rely on doing just simulations? How effective are these?
So, see, this is like a controversial question. I mean, different people might tell you different things. I am enough of a physicist that I would say I think the ultimate test is always the experiment. So, of course, DFT is not always perfect. There are systems for which it fails. We are beginning to learn why it fails, and we also are beginning to learn how to do calculations for those systems. But the ultimate test is always the experiment. And of course, especially if you're designing materials, you ultimately want to make those materials. So you have to do it. But I think in the context of, of women in science, I do have to say that this is perhaps a good field to go into if you have constraints that do not enable you to spend a lot of time in the lab. I mean, I have a postdoc in my group right now, a female postdoc who has 2 young children. And during especially the COVID times, it was very difficult for her for various family reasons to come in to work. She initially was an experimentalist. She did her PhD in experiment, but she decided to switch to DFT full time because she realized that with the various personal constraints she had, it would be easier to do this kind of work. Of course, she does have access to our powerful computer resources, but the fact remains that she can do these calculations while working from home. It's still extremely hard for her, of course. Sometimes, I mean, she's looking after her kids all day and she's working late at night, etc. But she's still, at least she can do that, which she wouldn't be able to do if she was doing lab work.
Thanks. I mean, yeah, I understand that. And thanks a lot. That was a lovely talk.
I have one question, Shobana.
Yeah.
Since you talked about adding the atoms and seeing the effect of it, you did mention there are sometimes the clusters.
Yeah.
So how does can you estimate the influence of the cluster structure? Because we know that in physics, a lot of systems show this cluster phenomena, and there are kind of magic numbers for the clusters like C60.
Yeah. So we obviously, the structure is hugely important. So different isomers, for example, will have different properties. So it's not just the number of atoms that matters, also the structure is important. And finding the structure of clusters, it's itself a huge problem, because that's the structure determination problem, because you have a lot of local minima, etc., which you can get stuck in. But the reason why the properties change so much at that ultra small scale when you add or subtract an atom is precisely because the cluster structure changes a lot with one adding or subtracting just one atom. So the environment of each atom changes a lot, as a result of which its electronic properties also change a lot. And that is why the properties are so size dependent.
So do you also see kind of odd even effects, like the things like atoms like pair or very prominently?
Yes, sometimes. It depends what you're looking at. For certain properties, you see odd even effects. For certain properties, you see these, what you said, magic numbers, shell closing. It depends what property you're looking at.
Okay. We'll just see for a couple of minutes if there are any more questions from the audience. While we wait for that, I have another slightly somewhat offbeat question, Shobana. You touched upon your trajectory. You also talked about your, the certain advantages in doing it right now, like working from home and the area. But, and also you are involved in this ICTP conference. So in your perspective, do you think that things changed a lot for the younger generation from about 2 decades back to now?
I think they have changed in some ways and not changed in other ways. I think when I was starting out, the whole idea of talking about women in science was itself strange. I had experiences that I don't think would be considered acceptable today. I mean, people at conferences passing comments, like, I'm talking to a prospective employer at a conference, and then somebody else passes by and says, oh, yes, I trust you to find the pretty girls to talk to at the conference, and, worse things also. And somebody from IBM came to Harvard looking for people to hire, and he saw me and he asked, so you're the secretary, are you? And, these kinds of things, I think that they probably still happen, but not quite so often. I think there's some amount of sensitization, even if it's just due to this feeling of political correctness. I mean, I don't think that's a bad thing. If people keep quiet because they realize they have to be politically correct, that's still better than they're saying multiple things. I think the numbers are slightly better, but and there are various schemes by the government in India. I've seen these schemes have been introduced over the time of my career. For example, paternity leave was something that was introduced in India over the last 20 years. So these little steps are there, but I still see my female group members really struggling. Not scientifically, of course, they're fantastic scientifically, but I see how hard it is for them to balance a career and family, to balance personal and professional commitment. And many of them are really debating with themselves whether to continue in science or not. And this I find really frustrating. I find, why is it that even today it's the women who are grappling with these issues and not the men? I mean, this should be an issue for everybody equally. And so I find that a bit frustrating.
Since we do have a couple of minutes, I'll ask one more question. Actually, it was probably yesterday I wanted to ask in the panel discussion. One aspect which even I think the women students all face it also more often than senior people like us, but perhaps because we get used to it, is, or we get used to dealing with it, is your small mistakes. If you are a girl or you're a woman, your small mistakes kind of get amplified. And this puts an extra pressure for performing. So do you think that is also true at a research level? And that's something which requires a change in the attitude of the people surrounding you.
I think that's true. And also you bear this extra burden. I mean, if you make a small mistake, if a woman makes a mistake, people don't just say, oh, she made a mistake. They have a tendency to say things like, see, girls can't do physics, see, women can't do physics. So you bear this additional burden that you're not just responsible for your reputation, you're responsible for the reputation of half of humanity, and that's a really unfair burden to bear. There's I don't know how many of you know this comic strip called XKCD. There's this XKCD cartoon where somebody does an integral wrong, and it shows a girl doing the integral wrong and a boy doing the integral wrong, or a man and woman. You can't tell because they're stick figures. And when the woman does it wrong, when the man does it wrong, someone says, wow, you suck at math. But when the woman does it wrong, they say, wow, girls really suck at math. So there are all these issues. And I do sometimes feel that people, judge women by a different yardstick than they judge men.
Sure. Okay, I don't see any more hands raised, so there are no more questions. So thank you, Shobana, once again, for really a very nice and...
It's my pleasure. Thank you.
Yeah. And we move on now to the second part, today's second talk. We have the speaker with us, Professor Eva Silverstein. She has joined us. So to introduce today's second speaker, I'll now invite Dr. Navamita Banerjee, a bright young physicist. She is presently an associate professor at IIT Bhopal. She did her PhD at Harishchandra Research Institute and postdoc studies at Utrecht and Amsterdam. She specializes in string theory, in particular in quantum gravity in 3 and 4 dimensions and black hole physics. So Navamita, please, to introduce the speaker.
Thanks a lot, Vandana. Am I audible?
Yeah.
Okay. So thanks a lot for giving me this opportunity to introduce Professor Eva Silverstein in this webinar, and particularly since it is a IPA and APS joint venture towards gender equity and new directions and steps. I definitely believe that we need new directions and we have to take bold steps if we want to go ahead. So let us get back to Professor Silverstein. Professor Silverstein is a renowned theoretical physicist, cosmologist, and string theorist And I would request you to please keep this order in mind while I introduce her to all of you. So she did her initial studies from Harvard University and then followed by her PhD studies from Princeton, where she worked with Edward Witten. And she wrote her thesis on singularities and n=1 string vacuous. So after PhD, she did her postdoctoral studies from Rutgers, and then she joined Stanford. Currently, she is a professor there at Stanford, and also she jointly holds the position at University of California. So let me now get back to her research achievements, which is awesome and very, very inspiring for all of us. So her work, which is very much related to string theory, is on tachyon condensation, and it's a landmark work in itself. And now she has also worked on predictable and testable mechanisms for understanding UV sensitive properties of observational cosmology and de Sitter gravity, and all are like extremely exciting. Even today, she is going to tell us on her work on cosmological horizons and informations. So that's going to be very, very exciting again. She also has done extremely interesting works on black hole physics. So now let me just remind ourselves that her quest of understanding fundamental issues of physics truly makes her a theoretical physicist. So she started her career as a string theorist, then really did extremely good work in cosmology. And overall, I do see her as a theoretical physicist. So it's really excellent and awesome. She has got many awards, and like I probably wouldn't waste more time, and I will welcome Professor Eva Silverstein to begin her talk. Thank you.
Well, thank you very much for that extremely kind introduction. I appreciate it, and I'm very glad to see you here. Yeah, we share a very interesting journey trying to understand many difficult questions. So let me share my screen. Let me see where it is. There we go. Okay, so you can see that, I hope.
Yes.
Okay, so now let me do the slideshow. Okay, are we good?
Yeah.
Okay, so I'm going to try and give you a kind of survey of what's going on along this theme of cosmological horizons and information. And because it's a general talk, I'll kind of split it up into two parts that roughly divide into real experiments or observations and thought experiments, which, as I think everyone knows, also have a storied history in our subject. And they both have to do with how the cosmological horizon carries information of interest to us in physics in rather different ways. So that's the general theme of the talk. So as I believe everybody is well aware, the universe is accelerating, and this was detected by a combination of measurements of cosmological observables. It was news over 20 years ago. Now it's very familiar. And at that time, these independent measures of the expansion history all converged. They agreed on the presence of a new parameter in cosmology, often called lambda, which governs the rate of the accelerated expansion of the universe detected in the late universe. And we can think of it as of order the square of the Hubble expansion rate. And it's famously tiny in units of the scale and Planck at which gravitation becomes strongly interacting. So that is a major piece of our cosmological standard model. Similarly, in the early universe, there's a lot of evidence, rather more detailed evidence in some sense, for there having been a period of accelerated expansion back then, nearly 14 billion years ago. I'll flash some of the evidence for that observationally shortly. And the theory of this is known as inflation, where you have accelerated expansion of the universe, which is driven by a time-dependent source of energy, which is most simply modeled as some sort of scalar potential energy V of phi being the scalar field active in the early universe known as the inflaton field. And in general relativity, our theory of gravity, energy sources cause space-time to curve, and that includes expansion. And this inflationary theory involves a source of nearly constant potential energy that drives nearly exponential expansion in the early universe at a much higher rate than that in the late universe. We don't know exactly the rate. We only have some interesting but somewhat weak constraints on it. And that was first proposed as kind of a solution to various macroscopic puzzles having to do with us seeing homogeneity, isotropy of the microwave background radiation from all directions, despite it being the case that if we didn't have accelerated expansion, the sources of those modes we see would never have been in contact, and it was quite mysterious. Instead, if we have this early acceleration, then we can imagine a causal source for those isotropic modes that we see in cosmology. So for these kind of macroscopic reasons, the theory of inflation was proposed, and it has an absolutely beautiful consequence, which is to do with the essential quantum fluctuations of this field phi. This field was introduced first to just give a time dependence to the potential energy, but as a quantum degree of freedom that can vary spatially, it does vary spatially according to quantum mechanics, according to the uncertainty principle, and those essential irreducible quantum fluctuations in the context of this accelerated expansion of the universe quickly spread out beyond the observable region of the universe at that time. And this we call freeze out. The modes become very nearly constant, so that they survive over the evolution of the universe until this period ends. And then they re-enter our observable patch as small fluctuations that are capable of seeding structure. And there's a very detailed theory of how that really works, which fits the data brilliantly. So moving to the right panel here, through work of many, many theorists and observers working quite in tandem on this problem, there developed a theoretical prediction for exactly how that should look in the late universe. Here is plotted the microwave background as a function of its scale or its Fourier mode. The power spectrum is called the 2-point correlations of temperature fluctuations that we see. And because of the intervening physics and the boundary condition from this frozen out mode, you expect to see this detailed structure of peaks. And although this has a lot of structure, it's fit by a simple 6-parameter cosmological model that is very non-trivially consistent with this hypothesis of the inflaton field being there, fluctuating according to quantum theory, and seeding structure that we now see. Okay, so this had to do with this theme I'm building up of horizons, in this sense that these modes are created as in a way that's associated with the cosmological horizon. There's a similar thing. Quantum fields in general obey this uncertainty principle, just like all degrees of freedom in physics. And in black hole physics, this leads also to something similar, which is the famous Hawking radiation, where modes are created in a way that's associated with the black hole horizon. You can very roughly think of it as modes falling in and another partner falling out or going out of the black hole. And so these two phenomena are somewhat similar. This Hawking radiation one has not been observed. It's difficult to observe unless there are primordial black holes of exactly the right range of masses, which could be true, but we don't have any, don't necessarily need to be there. But as a theoretical physics calculation, it's very, very compelling. However, it leads to a famous problem, the information problem, that this simplest calculation leads to a featureless radiation just determined by an underlying temperature. And yet the black hole could have been formed by anything. And so we'll come back to that information issue a bit later. For now, I'm just listing these interesting effects of horizons on the behavior of quantum fields in their vicinity, with Hawking radiation being one example, and the quantum fluctuations that seed all structure in the universe being another. So this little image illustrates the evolution from inflation with those little fluctuations to all the detailed and rich structure that we see today, which fits the facts very, very nicely. So because it fits those facts so nicely, it actually supports much further work extracting information about the dynamics going on all that time ago, the 14 billion years ago, in the sense of extracting more details about the inflaton dynamics, which is interesting in itself. But there's something important about it that motivated quite a number of us to pursue it, even though, as was described, some of us started our lives as pure string theorists and entered into cosmology in part for the following reason. This behavior of the inflaton field to have this potential energy that supports accelerated expansion in the early universe for a significant but finite period of time requires certain properties of its potential energy V. Basically, it needs to be, there are variants of this, in fact, variants of this that we discovered via string theory, but in one version of inflationary theory, these ratios of the derivatives of the potential to its value in Planck units, first and second derivatives, must be quite small. That's just saying that it supports inflation for a sufficient period of time to develop a large universe out of a very, very small one. And if you study these formulas and you imagine you have a theory of inflation that works, but then what you do is you add something to the potential energy that could, for all you know, could be there. Something that, say, starts with your original hypothesis for this and adds to it that times a quadratic ratio of this field phi minus wherever you are on its potential energy phi naught squared, let's say, divided by m Planck squared. So such a term could be there in the potential energy. And since it involves this strong coupling scale of gravity, it's a form of a quantum gravity effect. And if you take this addition and calculate these so-called slow roll parameters, which we said need to be small, you find that they actually correct it in a way that's order one. So turning that around, it's saying that to have a true understanding of inflationary theory requires control of these sorts of quantum gravity effects. And partly for that reason, and partly, frankly, just kind of serendipitously, a number of us have stumbled upon interesting mechanisms for inflation that descend out of string theory, could have been discovered at some level by what we call low energy effective quantum field theory, but it was much easier to discover them in string theory for various reasons. And they lead to these novel mechanisms for inflation, which are actually observationally testable. So when I entered the field, the questions involved in string theory and quantum gravity were and continue to be sufficient motivation to work on the subject. But it was thought that, you know, good luck having anything testable within your lifetime. So it was a wonderful surprise to realize that is in fact not the case in early universe physics, that there are very well defined predictions that we can make that are model dependent. These are not grand predictions of string theory as a whole. Don't believe it if anyone tries to sell you such things at such a grand scale, but at a model dependent scale, there are meaningful tests of even string theoretic dynamics that we can perform in early universe physics. Okay, so there's more information to be had, in other words, about these modes from these fingerprints of the early universe that we see via the freeze out of those early universe modes. One thing that we can do with that to get a little bit more detailed is to study a bit more about the statistics of the perturbations. So we all know that Gaussian distributions can be valid approximations, central limit theorem, for example. And in this context, there's tests of the Gaussianity of these perturbations, tests of whether indeed the 2-point correlation function is actually a good approximation, that have tested that along certain parameter directions. And it's a good approximation, but not good enough to exclude many forms of what we, for lack of a better term, call non-Gaussianity. In general, there's some wave function for the fields that operated in the early universe, just like there is in ordinary quantum mechanics. And the square of that wave function gives the probability distribution. And it's from that probability distribution that we draw the modes that we see in our part of the universe, our accessible part of the universe. And the beautiful thing about this is that it is sensitive to the dynamics in the early universe, things like the sheer number of fields that were involved and their interactions. So it's really a very special case for which this is truly Gaussian. And so one of the types of observables that we discuss is indeed this non-Gaussianity that arises in a variety of ways, some of which were really discovered again via string theory, via a certain sort of dynamics that it introduces called DBI dynamics as one example. But there are by now many interesting signatures that one can develop templates for and test against the data, microwave background data, and also increasing data sets that capture more and more of the large scale structure in the universe. And it's actually a really interesting theoretical problem to take that data, which in principle has enormous information about things like this, and really extract it, which means to separate primordial signals of this sort from the ordinary nonlinearities of general relativity and standard model physics. So that's yet another example of this theme of information in cosmology. So there's this non-Gaussian distribution to try and unravel. There's another quantity which is of great interest, which is the strength of gravitational fluctuations of this sort. So in addition to the inflaton field's own fluctuations, we have gravitation, and we have the gravitational particles known as gravitons or tensor modes, which also fluctuate at some level. And that amplitude is this axis R here. The precise way that the inflation evolves with time is related to this horizontal axis, the tilt. And from this quantum gravity point of view, or brought down to Earth via a field theory description, we can understand kind of trends in the data relating to effects in the theory. So for example, in this plot of the amplitude of the gravitational waves versus the tilt of the spectrum, if you take into account that your so-called UV theory, in this context, let's say string theory, has generally many degrees of freedom that might be quite heavy that we don't see directly, but which adjust during the process of inflation, they inevitably kind of flatten the potential out because that is the energetically favorable thing for them to do. And that pushes this direction in this plot. If you add additional field sectors, and one part of the baggage of string theory is that it has quite a rich set of particles in general, including many copies of the same sorts of fields typically. So if you fold that in and you look at what it does in this plot, it pushes things in this direction. Okay, so there's some very simple ways to interpret the data. It's extremely exciting to see the observations push further and further in this plot, and it helps us discriminate among different possibilities for inflation in a quite serious way. On the other hand, it's limited. It's 10 to the 6 modes in the CMB, and it's not that we can exactly flesh out what this functional is or anything like that, but we can make meaningful distinctions between different, quite qualitatively different scenarios for that dynamics going on so long ago. Okay, so coming back to that wave function, one of the things going on now in various groups, including ours, is to understand this probability distribution beyond the sort of low point correlation functions, and to understand the shape of the tail of the distribution. In fact, that varies a lot by models as well. And so there are cases where it can be quite a heavy tail, and one can develop methods to look for that in the data. Okay, I won't go through specifics of that, but just know that there are examples of that are sensitive to heavy fields, that those then became understood at the level of probing the data for them. The so-called optimal estimator was developed by these authors, and there's a program to pursue that in the various data sets. There's a much different example of the strength of the tail of the distribution coming from effects of additional fields like those I mentioned earlier. And various groups are studying that either analytically, as we like to do, or with massive simulations to try and understand the structure of the quantum field theory non-perturbatively in the tail of this distribution, and as a consequence, how it might or might not show up in the data. Okay, so that concludes part one, which was meant to be a kind of quick overview of some things going on in extracting information from the cosmic horizon that seeded structure in the early universe. And in particular, I focused on how it is a very solid foundation for further tests of microphysics. And even more specifically, we can now move on to interesting non-perturbative aspects of this to try and make the most of the data. Okay, so that's, as I say, concludes the first part, which was real observations. Now we're going to move to abstract matters, thought experiments, and along the same lines of the horizon and information. Okay, so in general, as we've already touched on, general relativity, our beautiful theory of gravity that has that works on a broad range of scales, predicts horizons when you look at the solutions to its equations. Famously, we have the black hole horizon and the cosmological horizon. So for a black hole, we theorists, on both sides of this slide, often use what's called a Penrose diagram, where we kind of flatten the geometry to something where we keep the speed of light front and center as a 45-degree line in our diagram of the space-time, so we can see the causal structure. So nothing can move faster than light. And so in this picture of a black hole, if you start to the left, or the upper left of this 45-degree line, which is the horizon, at the classical level, which this picture depicts, you cannot get out of the black hole. Similarly, so the more intuitive picture of the black hole is you had a bunch of matter well flat. And logical horizon is accelerated of the universe depicted here. So nearby separate exponentially, eventually lose causal contact. And in a, can you confirm that you can still hear me? I'm getting that my internet is unstable.
Yes, you are audible. Yeah.
Okay. Okay. Thank you. No, I just got a warning. Okay. So in the right-hand picture, we're talking about the cosmological horizon and the accelerated expansion and the observers losing contact. And that's actually depicted also in this so-called Penrose diagram, where if I'm an observer here, I simply have no access to the left side of the picture because of light going on these 45-degree lines. Okay, and this is the situation we're in real life. Theorists spend a lot of time, more than I would think is healthy, on the other side of the cosmological constant, but we'll discuss aspects of both in the remainder of this session. Okay, so back in the 70s, there were extremely interesting results coming out of theorist calculations of the dynamics of black holes and also the cosmological case. But let's say for black holes, what people found in working with the equations of motion of general relativity is that these black holes, not only do there exist solutions, but they can be studied, in quite a bit of depth, finding that as they evolve, as they merge, for example, they obey certain laws, like this one that describes the change in the mass of the black hole relating to the change in the area of its horizon. And there are similar terms of this form involving the charge and the spin of the black hole. And one thing that was true always is that the total area always increased. And it was noticed that these equations on the left are the spitting image of thermodynamic equations in regular physics. So I guess the first law, it's called dE equals TdS plus stuff of the same form, and the entropy increasing. So this suggested that indeed the area of a horizon of a black hole, if you're careful about it in units of M Planck or G Newton, as written here, with a particular factor 1/4, corresponds to the entropy of something to do with a black hole. Classically, we have this piece. There's also quantum fields around that fluctuate in the way that we discussed earlier. And so this raised a very interesting question. Can we make precise this idea that there's an entropy associated with this area plus quantum field contributions to it? In particular, it suggests that there's a finite number of states that are associated with a black hole, and the energy levels in particular should be discrete, not continuous. Okay, so long story short, that works out, at least in calculable situations, again, in string theory, which is our leading theory of quantum gravity. So in particular examples, it was the case that people could assemble black holes out of the nuts and bolts of string theory, which includes strings and also higher dimensional defects known as branes, and putting those together in some way with a quite a lot of extra unrealistic symmetry, but still doing so in a way that produced a black hole, led to a precise count of the entropy as a state count, as a micro state count, we call it, where indeed the area agrees with this count of states. And this subject, there are many contributions to it. I just kind of depicting a few updates. One can relate it quite a bit to very sophisticated mathematical notions in number theory, for example, and find over and over again that it does fit in these calculable cases. And people also revert to kind of toy models where they can do more calculations even than that and get a sense of the discreteness of the spectrum. which, by the way, involves level splittings that are exponentially small in this number. So that was a beautiful development in the field over the years. It led to, among other things, the famous ADS CFT correspondence, where now we talk about the opposite sign of the cosmological constant. It's actually kind of funny because this, as a theoretical idea, was discovered basically 1 year before the true answer was discovered observationally to be positive. So this had a head start in the theoretical physics world. In any case, it's a wonderful toy model for quantum gravity, and has been developed massively over the intervening years. And how it works is that for this sign of the cosmological constant, again, invoking one of these Penrose diagrams, one finds that, first of all, the symmetries of the theory and many, many other detailed calculations match an idea that the ADS system, which is the solution or the set of solutions to this problem in gravity, match observables of a different, a priori different system, a conformal field theory, a special kind of quantum field theory, which does not have gravity and lives in one lower dimension. So we went from D+1 to D. So in some sense, what we call the radial dimension of this space-time is emergent. And although it sounds wild on first glance, there's an enormous amount of evidence for this statement. And it's very much in the spirit of what we already covered here, that we might expect an area's worth of degrees of freedom to capture gravitational physics. And then this is kind of the culmination of that idea, where rather than having a volume's worth of degrees of freedom that we need to formulate the system, we only need one less dimension's worth to do that. And so in this sense, we have a theory of quantum gravity emerging from this non-gravitational conformal field theory. Okay, so there's a lot of evidence for it, I said, but there's also still much to do to understand it in detail. And it's not just niggling details, it's things like the black hole information problem that I mentioned earlier. And also we need to upgrade it to the real world case. The real world case is not only, dictated to us by observations, which would be reason enough, but it's also, much, infinitely more generic in string theory. Most sources of stress energy are positive, and there are very large sequences of examples of this case that involve those positive sources of energy in the theory. Okay, so we want to understand it better. So let's continue a bit with the wrong sign of the cosmological constant and say a little bit more about how it is that we do that sort of probe of this idea of the emergence of space-time in the radial direction of this Penrose diagram. So the idea is that the CFT is the simple quantum mechanical operators are associated with the boundary of the space. And then if you want to reconstruct something that goes toward the middle of the space, you need longer and longer length scale degrees of freedom. And a kind of more complex description from the field theory point of view gives you the physics further and further in this emergent geometry. There are ways to probe it involving the famous brains of the system that I mentioned to you, where if you consider some defect that's flying around in the space, it obeys relativity, and that alone is telling you something about motion in the field space of the dual conformal field theory, building up basically the Born-Infeld dynamics. So that's another way to probe it. And various entanglement entropy calculations also involve ways to probe into the space-time. So if you compute something like the entanglement between two separate regions in the field theory, which is another notion of information, of course, you find that it's, again, related to a kind of area of a surface that extends into the bulk of the space-time. And so that, as you might imagine, just from this statement, gives you another way to probe the so-called duality dictionary, the way to the way that the space-time emerges. Okay, and one theme in the subject is that entanglement, in fact, is very much very strong when regions of space-time are connected to each other, as is familiar in ordinary gravity. And there's evidence for that statement. It's not just a wild philosophy, although making it precise remains difficult. Something like that also happens for positive cosmological constant. Okay, so coming back to this version of information in space-time, the black hole information problem, there the problem was, as I mentioned, that we can form a black hole with anything, and then the Hawking radiation, which is a beautiful effect, only depends on a few quantities. In the simplest case, it just depends on the mass of the black hole and nothing else. That translates into the temperature of the radiation. It looks kind of like a thermal spectrum. And if it really were that way throughout the process, that is, if it kept evaporating without any carrying any information, then the entanglement between the radiation and the black hole would just continue to grow, even as the thing evaporated entirely. But if it evaporates entirely, we're back to having a pure state. We don't have this division between modes inside and outside the horizon. And so if it's an ordinary quantum system, as it should be, according to this ADS-CFT correspondence, because in that correspondence, we just have some quantum field theory that really constitutes the system, and that is perfectly consistent with ordinary quantum mechanics, with unitarity and pure states. So the prediction of ADS-CFT would basically be that the radiation, the entropy of the radiation follows a curve known as the Page curve, which goes up for a while as per Hawking, but then goes down. And there's been progress on that. So taking seriously the expression for the entropy in terms of area plus the behavior, the contributions of quantum fields in the space-time has led to a prescription that reproduces this Page curve in a way that uses, where was it? It uses this term in my equation it plays a more dominant role than one might have guessed initially. And with that, people find this curve. This is good news. It's another check of information really being there in a subtle way, but there's a lot of open questions about it, and the detailed mechanism of how this works in real time is not fully understood. Okay, but I'm personally much more interested in the issue of upgrading the whole thing to the correct sign of the cosmological constant, and we've had some quite renewed traction on that in recent years. So I'm going to finish this lecture by trying to communicate a little bit of that to you. Okay, so the motivation is hopefully completely obvious. The real world has this property, and I'm telling you that in string theory, most of the time we have positive potential energy. So if we want to understand either quantum gravity or nature, we had better understand this case. Let's proceed as follows. I described to you how it is that the boundary of ADS corresponded to short distance modes, the high energy physics of the CFT. And as we went toward the middle of the space, we were getting lower energy physics, long distance observables. And so with this anti-de Sitter space, one thing I should stress about it, which I should have said earlier, is that as we go out to this boundary, although we kind of flattened it in this Penrose diagram sense, as you go out to the boundary, the actual distance out there is infinite. So it has this kind of boundary formally, but it's unrealistic in many ways. For one, it has the wrong sign of the cosmological constant, and unlike the de Sitter hyperboloid, which is constant and which is finite at any finite time, this thing has is an infinite space. Okay, so because of that, one approach would be to at least get rid of this highly unphysical boundary, and that involves mucking in some way with the high energy physics of the theory, the short distance physics of the theory. And in a really, really amazing development, for quite different reasons, other theorists, Zamolodchikov, who's a hero of our field, and many others, developed a certain understanding of deformations of quantum field theories, including these CFT theories, which muck with the short distance physics of the theory in a way that they found quite calculable, despite it actually being a much more difficult case to cover in quantum field theory, to understand what's going on if you start adding contributions to the Hamiltonian of the system that affect it in the high energy regime. So there's a particular way that you can add such a deformation. It's called TT bar. It involves the stress energy T in the theory, which for which not only does it affect the ultraviolet part of the theory, it does so in a calculable way. And it does so in a way that whose calculable energy spectrum agrees precisely with what you get if you bring in the boundary and not include the very unrealistic high energy part of the boundary. Then with some friends in theoretical physics, we generalized that to include a very easy deformation of that deformation, which is equally calculable. And in that case, with this extra parameter, the deformation can be set up so that it builds up not just the geometry of a finite patch of the anti-de Sitter space, but actually converts it into a finite patch of the de Sitter space. So we get a reconstruction of the correct geometry in this calculable way. And very, very recently, we found a count of microstates that we could obtain in that manner in a very explicit and calculable way. So there's a certain deformation of conformal field theories, which produces two results. It gives the geometry of de Sitter. I think we're running out of time, so I'm going to skip to a kind of picture of all this. It gives the geometry of de Sitter in an observer region that is accessible to an observer, and builds up the geometry of such a patch that is bounded by a finite amount, while at the same time capturing the microstates. And it proceeds by starting with our understanding of the microstates of a black hole, performing this calculable deformation to a point where we're very near the horizon of the black hole. And when you're near the horizon of such a black hole, you can't tell the difference between that and being near other horizons. In particular, you can't tell the difference between being at that horizon or a cosmic horizon, at which point we can turn on our new contribution to this kind of deformation to build up the geometry of de Sitter. And in this business, thanks to the methods of Zamolodchikov and company that we extend to this other contribution, we can calculate the energy spectrum of the theory and check that it agrees with the general relativistic notion of energy due to Brown and York in such a patch of space-time. And at the same time, the energy levels have a certain, not quite degeneracy, but a certain count that goes along for the ride in this deformation. So the correct count of states in the black hole extends to the correct count of states for the de Sitter observer horizon. Okay, so let me go back just to reiterate that here we are interested in the analogous question that we talked about in black hole physics for the cosmological horizon. So similar to those black hole thermodynamics manipulations I mentioned earlier, similar calculations somewhat more vaguely suggest, but do suggest a thermodynamic interpretation of the observer horizon in cosmology. And it's a thermodynamic interpretation in which the entropy would be the area of the horizon surrounding a given observer. And by the way, there are calculations not just of the leading contribution to that, but some sub-leading contribution. And what I'm explaining here too quickly, but just to give you a taste, is that that question is amenable to very modern tools, in particular, this so-called TT bar deformation plus the lambda 2 contribution to it that we showed was equally solvable. And the upshot of all of that is that there is a way to understand the microscale counts of de Sitter at this level. The theory needs more input to capture all the physics of the system, but this leading contribution to the entropy is captured by a calculable deformation of a CFT. Okay, so I think I'm at the end of the session, so let me just conclude. The theme again was cosmological horizons and information, and we treated that in two ways. One is real observations and what information we can glean from those. And, there are very wonderful opportunities there that involve observation and theory to extract the most meaningful information that we can from the early universe. And then in thought experiments, we have the analog of black hole thermodynamics for the cosmological horizon, and we have been enjoying some renewed traction on that problem, thanks to the coincidence of developments in string theory, in quantum field theory, and its deformations. So with that, let me conclude and invite questions.
Thanks a lot, Eva. Thank you for the talk. So we can go for the question sessions. Bandana, will you please first ask the question from YouTube, please?
Okay. So the question on the YouTube is that will the physics of black hole? Okay, sorry. The first part is, why does the standard model break down as it approaches the black hole? And will the physics of black hole bring the new era of physics?
So the standard model, let's go slowly with this question. It's a great question. There's nothing about black holes that breaks the standard model of cosmology or particle physics or gravity. There's wonderful probes or measure, detections of properties of black holes through LIGO and through the Event Horizon Telescope going on. I'm sure you've all seen the image from the latter and the beautiful events from the former. And although, there are creative ideas for beyond general relativity physics, there's zero evidence for any such breakdown. At the level of thought experiments, the problem is that for things, these thought experimental problems are not something where we're going to detect immediately a deviation from the particle content of the standard model or anything. However, there is room for some new physics happening at the horizon whose implications for these tests of near horizon physics could become interesting for phenomenology depending on the outcome of the theoretical calculations. So in the black hole information problem, I mentioned that there's progress in computing this page curves, but that we don't really know the real-time evolution mechanism for how the information comes out. And old arguments suggest it involves something somewhat non-local. It can be perfectly causal, but not the same physics as we have in quantum field theory as it underpins the standard model. I think that's kind of where this question is likely coming from. So first, what I was saying is, at the level of accessible phenomenology, there's no current deviation from the standard model. But from the thought experimental problem, since we don't understand precisely the mechanism for the information coming out, it is possible that it involves new physics that is not only interesting for us theorists, but also potentially relevant. That remains to be seen. One example of that is that the way strings interact has a very large longitudinal extent at high energies, and near black hole horizons, you have non-local high energy boosts between infallers. And so one of the developments is that that can bring about interactions at a much larger scale than would happen for ordinary particles. This is called longitudinal string spreading, but it remains to be seen whether that translates into some observable. I think it's worth understanding precisely what the leading effect is in the Kerr geometry, and that's actually a research program that's ongoing.
Thank you.
In the chat box. So Batuturi is asking that, do you include an artificial time-like boundary?
So I can't quite hear. Do you include?
Nabhanita, you were not clear. Could you repeat?
Yeah. Time-like boundary in d-theta, and what is the physical role?
Yeah, I guess in the Q&A, you can also read the question.
It's in the chat, is it? Okay.
No, it's in Q&A. I'll just read out to you in case your window is not open. It's from Batul. Thank you for the talk. Do you include an artificial time-like boundary in d-theta? What is the physical role of that?
Okay, that's a fantastic question. So, which gives me a chance to say a little more about this. Except now I've lost my. Okay. Sorry, I need to minimize all of you again. Okay, so yeah. So let me just spell out the question for other people first. Okay, so we have, ADS CFT, there's this boundary, it's time-like. So what the question means is this is something which is below the speed of light, this trajectory here. In de Sitter, the picture maybe doesn't make that super clear, but it's doesn't have a time-like boundary. It's a hyperboloid that globally would at late times, it has this exponential expansion. At early times, if you include the full evolution, it just contracts in a similar way. And it has no such boundary. Okay, so the question is asking, why are you talking about a bounded region of de Sitter, given that, unlike ADS, there is no boundary. So there are two ways to think about to explain why this is useful. One is as a building block. So what the TT bar plus lambda 2 deformation gives you is much like an ADS, once you start bringing in the boundary, and here we're following the work of McGuff, Mazet, and Verlinda, you get a finite patch of ADS. And what happens here just technically is that when you then go in the part of this deformation trajectory that includes this lambda 2, you start a evolution that buys you a patch of de Sitter in a similar way. And at this level, what you've got is at the level of these pure gravity degrees of freedom, you have a Dirichlet boundary condition for the metric on such boundaries. Let me go to this picture here. So for this patch, for example, we can formulate something that agrees at the level of these dressed energies with the Brown-York stress energy on a bounded region where we have simply put in a Dirichlet boundary condition, and we can move that all the way out to the observer position. Okay, so there are two ways you can think about why this is useful. One is to just do what I just said and think of it as conditioned on an observer being there, for which the Dirichlet wall is playing the role of the observer. So although de Sitter by itself has no boundary, if you think about an observer, a tiny little cylinder is like just adding an object there, an observer there that is is not giving you de Sitter by itself, it's giving you de Sitter condition on the presence of that observer. But another way to think about it is just as a building block. I'm sorry, I don't have all the slides for this, but you can take these types of patches and you can join them together ultimately and integrate over this fixed metric on the shared boundary, and do that throughout the system and build up the whole patch. So the whole global space-time, which in the end doesn't have a boundary. So without going on and on, this question is, I think, from an informed person, and I'm not sure that everyone would understand it, but the two ways to think about it, once again, are condition on an observer being there, which plays the role of this Dirichlet wall brought to, a tiny cylinder at the North Pole of de Sitter. So there's no boundary, but there is an observer sitting there. Or think about it as a building block, where in the end you formulate these patches and then you sew them together, integrate over their metric, and formulate the whole space.
Thank you. Nabamita, are you?
Yeah, Shujitala, please go ahead.
Okay. Can you hear me?
Yeah.
Yes.
Okay, great. So if you go to in the beginning of your talk, where you showed the N sub S R plot, the observational constraints, is it from the the Planck TT and T part spectrum, or? Yes. So it also
no,
has
this is actually, this should be updated a bit, because Bicep Keck came out with a new thing that shrinks this a bit.
So,
this has in it, Bicep Keck. Yeah. Okay.
So the question is, do you think that, so I think there's two parts to the question. Part A is that with the current CMB constraints, or constraints from a large-scale structure like Bayer, do you think multi-field inflation has been ruled out, or is it still a possibility? That's part A. And part B is, do you think there's a possibility to sort of update these constraints if we have measurement of the BB power spectrum, like the primordial B modes? So what's your thought on that? Do you think that the N sub S are plot and we can have more constraints on inflationary model?
We do have more constraints. I don't think it does not rule out multi-field. In fact, it pushes in this direction for, say, this type of model. Multi-field is helpful in the NSR constraints. So it does not eliminate multi-field in any way. The thing that one thing that probes multiple fields in some different ways is the so-called local non-Gaussianity, which is somewhat constrained but not fully constrained, and that depends on how well we do with large-scale structure. But it is true that this there's a certain class of single field, so not multi-field, monomial with interesting powers from this flattening effect. This kind of line is now under significant pressure. So the data has improved to where that's true. So I'm saying yes to your general question, but I'm saying I don't see why it doesn't exclude multi-field. It doesn't. If anything, in this case, it kind of points in that direction. And to do multiple field.
Yeah, please. Sorry, go ahead.
I mean, and then I'm saying there are other probes of various multiple field effects.
And so the BB, do you think that if we have measurement of the BB power spectrum, then do we expect to improve our constraints for example, in sub S and R thing?
Well, right now it's an upper bound. I mean, the likelihood has a peak, at some value that's maybe around here or something. But it's not significant at all. So it's an upper bound. We don't have a measurement of. We have a measurement of V modes, of course, from lensing and from the foregrounds generally. But I think I may be missing your question, because you have something in mind, I can tell. But
no, I think it's, I was talking about the primordial V modes.
We don't have a measurement of those.
Yeah, we don't have a measurement of those, but I think my question was, do you think that we can have additional information or constraints on this N sub S and R, if we have, I mean, what kind of additional constraints can we expect from the measurements of primordial P modes?
Oh, you mean how well is this going to do?
Yes. How well it's going to do. Sorry about that.
Okay, yeah. Well, some good news on that is that there's this decadal survey in astrophysics that highlighted the CMB stage 4, which is going to, of course, one never knows until one does it, right? But the hope is to get down to 10 to the minus 3 in R right now. I mean, to me, the most interesting regime is this one they're in now. They're getting towards. So I'm happy that stage 4 is planned, but even stage 3 is going to do a lot. You could read the science book for stage 4, and now that it's
it's available. Just came like a couple of days back.
Yeah, that's right. So it's I mean, it's a very serious program, and it seems likely to happen. I don't want to claim right here that it's going to get to that level, but it sounds it seems practical.
Okay.
I mean,
thank you.
Yeah, thank you.
Okay, am I audible?
Yeah, your voice is very slow, but yeah.
Okay, actually, sorry. I have a lot of disturbance. I'm sorry, Vandana. I have written a question. Okay. If possible, can you please read it out?
Yeah, sure. You can type the question. Yeah.
I have it. I have already typed it.
Okay, let me see where it is. I don't see it in the chat.
Oh, I see it. Can gravitational memory in de Sitter be measured? Is that the question?
Yeah.
Yeah, that's a very interesting question. Honestly, I haven't thought about it. I see the question. I like the question. I don't know. I haven't thought about it at all. It's a good question. Yeah, there's been a lot of discussion of that with kind of asymptotically flat boundary conditions and so on. So yeah, it's a very natural question. I'm sorry, I don't have anything useful on it.
No problem, Eva. Thanks a lot. Thank you.
Yeah, thank you.
I don't see any more questions. So let me thank Eva for a very informative talk. And let me also thank both the speakers for informative and inspiring talks. As I said, it will really be very motivating to all young researchers and particularly women. I also take this opportunity to thank APS and IPA for their support. In particular, Amy Flatten and Spencer Vadia, who played a very important role in facilitating this program. I thank my co-convener, Dr. Rennie Michelle Gordson, I hope I have pronounced the name correctly, for her proactive and enthusiastic engagement in this event. And greatly appreciate efforts of Alex, APS International Affairs team as a whole, Tanushri, Shubhaviti, Satyanarayan, and Madhurima for assistance in organization of this program. And a big thank you to all the participants today and yesterday, Zoom and YouTube, to attend this in spite of the inconvenient time, both for India and the US continent. So thank you very much. And we hope we will have more of IPA APS events in the coming years. Look forward to that. And good day and good night.
Thank you, Vandana. Thank you for your efforts.
Thank you.
Thank you.
Thanks. Bye-bye.